Welcome all. Today's session we will discuss about transformers. So all of you know that transformer is a device for converting a low alternating voltage at high current into a high alternating voltage at low current and vice versa. So it is an electrical device based on the principle of mutual induction between the coils. So all of you know that what is mutual induction. So when the current is running through a conductor will generate a magnetic field, and the changing magnetic field will induce a current. So next we discuss how we construct a transformer. A transformer consists of two coils called primary and secondary S, which are insulated from each other and wound on a common soft iron laminated core. So in this picture you can see the two coils are here, primary and secondary, which is wound on a laminated core, soft iron laminated core. So the alternating voltage which is to be transformed is connected to the primary, while the load is connected to the secondary. That is, we do the arrangements. So transformers which convert low voltages into higher voltages are called step-up transformers. So step-up transformers, which means step up, that means which convert low voltages into high voltages. High voltages. So next type is step down transformers. So which convert high voltages into low voltages. So these are the two type of transformers. So in a step up transformer we have to convert low voltages into high voltage. We usually do the arrangement that the turns in the primary will be thick and the number of turns will be very low compared to the secondary coils. Okay, so the secondary consists of large number of coils, which is the copper wire we usually use for using for as coil, and which is the number of wires or turns in this secondary will be very large. Okay, so compared to the primary. So these are the another point for the step up transformer. The primary coil consists of a few turns of thick insulated copper wire. So primary number in this step up transformer is the number of turns that we represent here is number of turns NP in the primary. So it is suffix P, which will be less than the number of turns in the secondary. Similarly, in step down transformers, the number of turns in the primary will be more than the number of turns in the secondary. So these are the main 2 points, comparison points for the step up and step down transformers. So now when an AC is applied to the primary coil, it sets up an alternating magnetic flux in the core, which also get linked with the secondary. So if there is any change in flux linked with the secondary coil, induces an alternating EMF in the secondary coil. So if there is any change here happen, the similar change will happen in the secondary also. So that will induced and primary in the secondary coil. So that means we can convert low voltage's value to the high voltage, that is a primary and secondary is connected with the magnetic flux lines. So if there is any change in primary, the same change will happen in the secondary also. So that will induce if there is any change in the magnetic flux lines, the alternating EMF is induced there. So we get the corresponding voltage in the secondary coil too. Okay, so now let us discuss about the how this change in magnetic flux line or number of turns and the current that produced from primary and secondary, all these are linked if there is we applied any load or there is no load connected in between the primary or secondary. So now discuss the main theory. The first one is transformer on no load. So in this you can see the picture, primary and secondary which is connected, but there is no load is applied to the primary coil and secondary coil. So let NP and NS be the number of turns in the primary. So we can write it here. So NP and NS be the number of turns in the primary and secondary respectively. So when an alternating EMF that is connected here is applied across the primary, a current flows in its winding and this develops a magnetic flux in the core. Okay, so here it is assumed that there are no losses and no leakage of flux. So then we can say that let phi be the magnetic flux linked with the each turn of the coil. Then this magnetic flux phi linked up with both primary and the secondary. So if there is if we apply any AC to the primary coil, there will be a magnetic flux linked with both the primary and the secondary. So as of you know, what is that, by Faraday's law of electromagnetic induction, the EMF induced in the primary will be obtained by the equation EMF for the primary we give the suffix P, and which will be the rate of change of flux lines, isn't it? So minus d by dt of flux lines in the primary. So it depends on the number of turns too. So NP and phi. So this is the equation. So we can write it as minus NP. The number of turns will be a constant. So change will be happen to the flux lines only. So minus dP by d phi. There is no. Okay. Minus NP into d phi by dt. So similarly we will get the equation for induced EMF in the secondary too. Okay, so induced EMF in secondary will be S will be equal to, the similar equation will come, d by dt ns phi, which is equal to ns minus and minus ns d by dt phi. Okay, so from this equation we can write the change in induced EMF. Okay, we can write the ratio between the EMF in the secondary and primary will be Ns by Np. So in an ideal transformer, we know the resistance of the primary circuit is negligible and there are no energy losses. So we for the ideal transformer we consider it like that. Okay, so the induced EMF epsilon P in the primary is numerically equal to the applied voltage EP across the primary. So we can write if the secondary also consider, secondary is an open circuit here, which is open here, so the resistance is infinite. So the voltage ES across the terminals of the secondary is equal to the induced EMF. So we can then write it as E is the applied voltage ES divided by EP will be equal to, which is directly equal to the induced EMF. Okay, so epsilon S will be epsilon P. So Ns by Np, which is equal to K. So where K is called the proportionality constant will come there, which is called the turn ratio or transformation ratio of the transformer. So K is a constant which is called turn ratio. Turn ratio or transformation ratio. So we can get the turn ratio or by just doing the Ns by Np, that is number of turns in the secondary, the ratio between number of turns in the secondary and the number of turns in the primary. So we can also get the value by using the applied voltage across secondary and the primary. So for a step up transformer, we already know Np is less than Ns and hence epsilon S will be greater than epsilon P. So we can write it as, in a step up transformer, epsilon S is greater than epsilon P and hence Ns is greater than Np. Similarly, for a step down transformer, epsilon S is less than epsilon P and hence Ns is less than Np. So now we will find out the current in the primary and secondary, how they are related to the number of turns in the coils, number of turns. Then let Ip and the Is be the currents in primary and secondary at any instant. Then we can say that the power will be equal to power in the primary circuit, power in primary and secondary we can write will be equal. Okay, secondary is equal, then we can write it as ES into IS will be equal to EP into IP. So we will take the ratios IP by IS, which is equal to ES by EP, and from the Freeman's equation we know epsilon S will be divided by epsilon P, which is equal to Ns by Np and which is equal to K. So these equations are, I get it now. Okay. So these are the equations. Just get it to this portion. This we already discussed. Okay, so you can see here the ratio is just reverse. So that is the thing you have to remember while doing the problems. Okay, all the other tens will be came similar, so this will be just remember while doing the problem. So when the voltage is stepped up, the current is correspondingly reduced in the same ratio and vice versa. So from this you can see when we stepped up the transformer, the current is correspondingly reduced in that time. Okay, and in the same ratio current will be reduced. That we find out from the theory. When we apply, there is no load in the circuit. When we consider, there is no load in the circuit. Okay, so then we'll just write the point here. Voltage is stepped up. The current is correspondingly reduced in the same ratio. Reduced in the same ratio. And vice versa. So in the step-up transformer, we can see that the voltage will reduce, so the current is correspondingly increased in the same ratio. So these are the things. Okay. Now let us discuss the transformer on load. The second case, when we applied load on the primary and the secondary. So transformer on load, you can see that there will be some load resistance. RP is connected to the primary and RS is connected to the secondary. Then we know that there will be the applied voltage will be equal to the induced EMF. We can write the it depends on the resistance too. So the current in the circuit, we can write the induced EMF will be equal to the potential drop across the resistance too. So we can write the back EMF equation in the primary coil like this: EP minus epsilon P, which is equal to the potential drop in the resistance, that will be IP into RP. So the back EMF equation for the primary will be EP minus IP RP. So this is the equation. So similarly, we will find out the equation for secondary, epsilon S, which is equal to for the secondary coil, ES equal to epsilon S minus IS into RS. The circuit is open circuit, so we will write it like this. So ES equal to epsilon S minus IS into RS. So epsilon S will be ES plus IS RS. So hence we will take the ratio epsilon S and epsilon P. We will write it as ES plus ISRS divided by EP minus IPRP. So this one will be equal to the turns ratio K, and we can write it as ES plus ISRS, which is equal to K into EP minus IP RP. And we will expand this, then we will get ES plus ISRS, which is equal to K into EP minus K into IPRP. I mean, take ES will be equal to, IS will come to this side, and we will write it as KAP and minus ISRS and we know that there is another equation from the last case, IP will be IP by IS equal to K. So from this equation we will write it as IP equal to KIS. So here IP equal to KIS means K square IS RP. So from that equation, KEP minus IS will be taken as common outside. So RS plus K square RP. So in this case, the energy loss ES by EP is not a constant but decreases as more current is drawn from the secondary circuit. So here you can see that ES by EP is not a constant but decreases as more current is drawn from the secondary circuit. As more current is drawn from secondary circuit. So these are the main points that we discussed in transformer case. So you can see that energy losses is also happening in transformers. The main losses were copper losses, losses in transformer. The first one is copper losses. So already you know the laminator the coil is made with the copper, so there's a loss of power due to Joule heating in the primary and secondary windings. Then the next one is due to the iron loss. So here the laminated core is made up with the soft irons. So this is due to the eddy currents being produced in the core of the transformer. So this can be minimized by using laminated iron cores. Next loss will be hysteresis loss. So during each cycle of AC, the core is taken through complete cycle of magnetization. So the energy expended in this process is finally converted into heat and is therefore wasted. This is minimized by using silicon iron for preparing the core. The hysteresis loop for this material is very narrow. Okay, so the another one is the leakage of magnetic flux. That is the fourth loss, leakage of magnetic flux. So due to leakage, all the magnetic flux produced in the core by the primary is not linked with the secondary. They may pass through air. The loss due to this cause is minimized by using a shell type of core. Okay, so that no magnetic flux will be leakage through the air. Next we discuss the use of transformers. The main use, you already know that for the electrical power distribution, usually we see in the roads for the step up and step down procedures of voltages, we need the transformers. So mainly for domestic and industrial purposes, for the electrical power transformation or distribution. Okay, next we used mainly for the audio frequency transformers, which are used in the radio receivers, radio telephony, radio telegraphy, and in televisions too we use the audio frequency transformers. Next one, the radio frequency transformers, which is mainly used for radio communications at frequencies of order of the megacycles. So next use we mainly used in the impedance transformers. This is mainly used for matching the impedance between two circuits in radio communications. Then another use for the constant current and constant voltage transformers, which are designed to give constant output current and voltage respectively even when the input voltage varies considerably. Okay, so these are the main uses of transformers. Thank you all.